Okay, so in order to understand the concept of integration by parts, we need to understand how to take the derivative of the product of two functions. It's something that we've worked with a great deal throughout the first semester, but in terms of its most general form, it would be the product of some function that we've called u. We could call u, and in other words, we could call v. You define it any way you want, but if we want to eventually build this rule, it kind of makes sense to call u and v. All right, so if I'm taking the derivative of a product, I would use the product rule. So first function u times the derivative of the second, dv dx, plus the second function v times the derivative of the first, which would be du dx.
These and u's are just similar.
They are. They are. That's why I try to put a little flair at the end of my u, a little pizzazz, a little extra oomph to distinguish it from the v. All right, so one thing I can do, just because I notice across the board, it seems like there's a dx everywhere. I can clear that out by multiplying everything by dx. If we're thinking in terms of equation solving, it's a technique that can be used. In which case I get d uv equals u dv plus v du. All right. Another thing I could do would be to integrate. You know, because if ultimately I'm trying to develop a rule for integration, I could do that. And now that I cleared out the dx's, I could take the antiderivative of both sides and come up with just a uv on the left-hand side. All right, so antiderivative of both sides. I could write that as uv on the left is equal to the I'm going to write them separately. Antiderivative of u dv plus the antiderivative of v du. All right, and a nice consequence of this is the fact that if I have a function and I can isolate a u, just like we do a U-Substitution, so I can identify an appropriate u, I might be able to find the antiderivative of that function using this information, because all our rule is here, our theorem, this integration by parts theorem is this equation solved for the antiderivative of u dv. Right? So all I would have to do is subtract off the integral of v du from both sides. And we arrive at this. All right, so a question that you might have is, why not solve it for v du? You could. Right? The person who created this formula opted to solve for u dv, right? The integral of u dv, right? Why not solve for u and v? Why not just leave it alone? Well, that would imply that you actually already knew what the antiderivatives were, so that could be a little trickier, right? Because when you're given an integral, you're given a function and a derivative component. So if that's the case, then you would want to have something that's in terms of a function and its derivative. Right? So through experimentation, through problem solving, we arrive at this one as being the better of the three possibilities. Right? So we'll play it out and see how it goes, because there's some cool applications of this down the line, but right now you might look at something as simple as the natural log of x dx. If I were to ask you what the natural log's antiderivative was, I mean, do you have that answer? Maybe you do. I mean, it's something you could memorize because it's one of the basic functions. We know the derivative of ln of x is what? 1 over x, but do we know the antiderivative?
Something plus c.
Something plus c, exactly. All right, so that's all we needed to know. So we can actually skip this topic now. No. No, I mean, I don't know too many people are looking at this and saying x ln x minus x. All right, that's, you know, unless you've already memorized that. All right, so let's take a look at this and see if we can use integration by parts to come up with the antiderivative of the natural log of x. All right, the little tips here, they're tips. They're not rules. And you know, you're always wary of things that start off with the word try. You can try this. Well, okay, so what happens if that doesn't work? We'll try something else. All right, so try letting dv be the most complicated part of the integrand that fits a basic integration rule. All right, so, and really if you kind of decode that and think about what it means, you're going to let dv be something that you can find the antiderivative of. Right? Because if you can't find its antiderivative, then you're going to be stuck immediately. Right? U is the portion of the integral whose derivative is a function simpler than u. But I'll even take a step back there and say, why don't we define u as a part of the integral that I can actually differentiate? Right? If I can't find its derivative, then I'm going to be stuck immediately. Right? So we want whatever our dv is to be anti-differentiable. And I don't mean in the textbook definition, I mean like in your own mind. Can I find the antiderivative? That's what we call an exclamation point.
Thank you, Matt.
And and for the u, can I find the derivative? And you may look at that and say, oh, why would I need to care about that? Why would I need to know that I can take the antiderivative of whatever I'm calling dv, or the derivative of the thing I'm calling u? It's going to come through in the process, because the first thing I'm going to do when I identify my u is find its antiderivative. I'm sorry, find its derivative. When I identify my dv, I'm going to find its antiderivative. So whatever u is, we're going to differentiate. Whatever dv is, we're going to anti-differentiate. Right? So we have within our integral, so our integrand is ln of x times dx. Part of that is going to become the u. Part of that is going to become the dv. All right. Would I want ln of x to become my dv? No, I don't know its antiderivative. That's why we're here. All right. So that's going to be my u, because I can find its derivative. The only other part of this integral that remains is the dx. So that would go with the dv. All right. So for the u equation, I'm going to take its derivative with respect to x. So that's going to become du dx equals 1 over x. Clean it up, just like we would with u sub. It becomes 1 over x dx. All right. And just like with u sub, you can skip that middle step if you want. Not required. All right. For the dv equals dx, I want to take the antiderivative. All right, remember there's understood ones in here. Antiderivative of 1 dv would be what? V. Antiderivative of 1 dx would be x. All right. We'll hold off on the plus c until the very end, because we have all this intermediate work. If we know that it's all going to consolidate into a single plus c at the end, why put plus c's all along the way? Save it for the end. All right. So now we're going to use our rule, and that is the antiderivative of u dv is equal to uv minus the integral of v du. All right, so the antiderivative of ln of x dx is equal to my u, which is ln of x, times my v, which is x, minus the integral of the v times du. Du is 1 over x dx. Can clean it up a little bit. So we have x ln x minus the integral of 1 dx. And so we get x ln x minus x plus c. All right, but it all comes down to what you define as your u and dv. Right? If you selected wrong, you would have hit a roadblock. You would have hit it immediately. First off, you would have come up with u equals dx, and then you would have stared at that and like, what is this asking me to do? And also, you would have had the more important part, dv equals ln of x. Again, we're using this technique for this question because we don't know the antiderivative of ln of x. That's why we're here. So we wouldn't put that in the part of the technique that requires us to know a fact about an antiderivative. All right, so that wouldn't make sense. All right, generally, that's how it's going to play out. We'll do a couple more together, but you might run into situations where it could go either way. Like in the next problem, you look at x and also e to the x, and you say, well, I can take the derivative or the antiderivative of those perfectly fine either way. They're both one is as easy as the other, right? So, what's the distinguishing factor? We'll talk about that in a second, right? So we have x e to the x dx. We have to define our u and also our dv. All right, so u and dv. Find I talk to myself more in this topic than any other time mathematically. Day to day, I talk to myself all the time. That's part of my psychosis, I think. So in this case, I would say, all right, so my u, could that be x? Well, yeah, sure, I could take the derivative of that. That would be very easy. Could it be e to the x? Well, yeah, also very easy. Which one is going to become simpler through the derivative process? Well, not e to the x, right? It's going to stay exactly the same, right? So the x will get simpler. So I would lean towards making my u x, because anytime I can make my situation simpler, I want to do that, all right? Also, I'd be thinking through the antiderivative process, I don't want to make things more complicated if I can avoid it. So while my derivative should make things simpler, my antiderivative should keep things from getting more complicated. And that works here because e to the x is not going to get any more complicated when I take the antiderivative. It's going to stay exactly the same. All right. The dx, that part, there's really no thinking there, because that dx is always going to go with the dv, because it doesn't make sense to have it with the u, because you would have du dx equals the second derivative of dx. That would just be, I don't know what that would accomplish. All right, so that would be kind of a useless step. All right, so u equals x. I take that derivative. I get du dx equals 1, but skip that step, make it du equals dx. Antiderivative. Again, there's the assumed 1 in front of the dv, making it v equals antiderivative e to the x is e to the x. All right? So our rule tells us that the integral of x e to the x dx, well, actually, that's a little ahead of myself here. u dv is equal to uv minus the integral of v du. Then in the next step, I can put the particulars in. So uv x e to the x minus the integral of e to the x dx. Right, just direct substitution all across the board. All right, my u goes with the v. The v is nice clean e to the x. And the du is nice, very nicely in this case, just a dx. Not always going to play out that way. right? Sometimes it's going to be a complicated expression. Sometimes you have to do the integration by parts more than once within the same problem. So you get to this step in the process, and the integral that you arrive at is something that you still have to integrate by parts, or use U-Substitution. Or it could be a simple integration technique like this one. So x e to the x minus e to the x plus c would be our antiderivative of the whole thing. All right. So in order to check this, you're going to a calculator or you're taking the derivative of this, but you can see product rule is naturally going to work its way in. Okay.
I have a question. I'm confused because in the first example, when we took the antiderivative of dx, we got x. But in the second equation, we took the antiderivative of ex dx. It was just ex, and the dx kind of just like disappeared.
Right, because the dx is really just telling us to take the antiderivative of the thing that precedes it.
Okay.
So in this case, it was telling us to take the antiderivative of 1.
Okay. So, okay. No, that's
All right, so the next one we have x squared ln of x dx. And this is going along the same lines where we want to simplify things when we take the derivative, and we want to keep from getting too complicated when we take the antiderivative. All right, so I have 3 ingredients here, the x squared, the ln of x, and the dx. So I can look at it, I could say x squared, well, that'd be great, I can make that u. When I take its derivative, it's going to get simpler, that's true. Right, but what about ln of x? Well, so let me ask you, what's going to be better as my u, x squared or the ln of x? Ln of x, because of the way I asked the question. Ln of x also because we just discovered what the antiderivative of ln of x is. That is the definition of getting more complicated. All right, the idea is to try, if whatever I'm going to define as my dv, through the antiderivative process, I don't want it to make things more complicated. Yeah, when I take the antiderivative of x squared, it's going to increase the power, but it's not making like a polynomial function into like an inverse trig function or something like that. All right, it's not becoming more complicated in that regard. Here, if I take the derivative of ln of x, it's making it into a rational function, simplifying it. If I take the antiderivative, it's becoming the difference of a transcendental function and a linear function. More complicated, all right?
If you did it either way, would you get the same result? Just more.
In a lot of cases, yes. In some cases, it'll break down.
Nice. I like that.
Yeah, the hope is that if it's going to break down, that it breaks down quickly. Like you're driving the car out of the dealership, and before you get onto the road, it breaks down. So you can say, hey, you sold me a crappy car. You want it to break down like that. You don't want it to break down like a month later. Then you got all sorts of headaches. I don't think I'm talking about calculus anymore. I think I'm talking about personal experiences. So. X squared dx is what I would define as my dv. All right, so my u, I differentiate that. It becomes du. E equals 1 over x dx. When I anti-differentiate, remember that's why I'm doing this over and over and over again, because I don't want people thinking that the dv magically becomes a v. Right? Again, it's taking the antiderivative of the thing that precedes it. In the next unit, we're going to get into the graphical aspects of antiderivatives, and you're going to see exactly in what way that dv makes that one integrate itself. But for now, we're looking at it as kind of a weird command. This is telling the one, take the antiderivative of yourself. Right? Just like that dx is telling the x squared, take the antiderivative of yourself. Right, so sounds rude when I say it that way. So 1/3 x cubed is equal to b. All right. So again, the rule: the integral of u dv is equal to uv minus the integral of v du. So we're looking at x squared ln of x dx is equal to, well, u and v multiplied is a little beefier now. Maybe want to put the v in front just for clarity. So 1/3 x cubed ln of x. It's fine because multiplication is commutative. Minus the integral of v du. Right? So 1/3 x cubed times 1/x dx. All right, so little cleaning, because this will simplify a little bit, which is nice. We want it to simplify a lot more, but we'll take what we can get. Oh, I'm throwing in an ln for some reason. I have no idea why. So the 1/x multiplied by the x cubed will give us an x squared. Now this is anti-differentiable through the reverse of the power rule, so that's perfectly fine. This is done, the left-hand side, so we're good there. This can be more complicated. Like I said, maybe you have to do U-sub, maybe you have to do integration by parts a second time. Maybe there's some other technique that you have to work through. It's all possible, right? And all things that we'll tackle as time goes on. So what are we looking at, 1/9? X cubed plus c. You know, in a lot of ways, this can be easier than U-substitution. It's just a question of identifying, and you'll see as we go forward, the big challenge in most cases is going to be knowing when to use what technique, because you might look at this and say, how do I know it's not U-sub? How do I know it's integration by parts? For the most part, you're looking for a product. If you see a product within a function, it could be integration by parts. So you try that technique. However, you see cases where we did the ln of x and we have arc sine of x dx where it's not a product. Right? And so in those circumstances, it's triage. You have to look at it and say, well, it can't be U-substitution because even if I got rid of the arc sine of x, there's nothing else to cancel out. So U-substitution wouldn't make sense here. Right? It's not a basic rule that I'm aware of, so I have to come up with something else. And there are rules that you can memorize because this is another basic function, but it's also something we can get with parts. So u and dv. All right, well, back to like the ln of x situation. Oh, wonderful. In this situation, just like the ln of x, we only have one function. Bless you. So that would have to be my u because I don't know the antiderivative of the arc sine of x, so I wouldn't put it as my dv. I was about to write ln. So arc sine of x, dv would be dx.
What are your thoughts on the other notation?
On the other?
Arc sine notation.
I can live with it. Yeah, it's perfectly fine either way. I like this one only because I don't get confused with powers and stuff, but you can go either way. Now the big challenge here in this question, or any question that's similar to this, is do you remember the derivative of the arc sine of x? There is a square root in there. One over the square root of 1 minus u squared. In this case, is all x's, so 1 minus x squared. And normally it would be u prime on top, but since x is the argument here, the derivative of that would just be a 1. So. All right, in the case of dv equals dx, again, it's the antiderivative of 1 dv equals the antiderivative of 1 dx, so v equals x. All right, so our rule, integral of u dv is equal to uv minus the integral of v du. so in this case, arc sine of x dx is equal to uv, so x, arc sine x. So it's arc sine of x. Been laying that gem on people for a good 15 years. Nobody's ever found it funny except for me.
What is it?
It's arc sine of x.
Oh, because of the, yep.
Yeah.
I get it.
Got it.
Oh, I
Yeah.
got it now.
Yeah, most people get it and then
Xerox?
find it not funny, but that's fine. It's just expected some kind of reaction, really.
Yes. Yes. Yes, you have.
All right, so uv minus the integral of v du, when I multiply the v and the du together, I get this beauty, the integral of x over the square root of 1 minus x squared.
You're welcome.
So then the question becomes, now what? It does smell that way. It's very pungent.
Was it mom?
It's a pungent odor.
Smells like you.
So,
Wow.
nice. Good. I don't even know.
Should we leave?
After
You make the joke.
integral of
Ollie.
du, is it dx or not x? The last one that you wrote.
Here?
Yeah.
So I'm multiplying this by this.
Oh, I see.
That's all right, so yeah, it's going to be U-substitution, and the way that we know that is because if I were to take the antiderivative of the expression contained within the radical, I would get a constant multiple of the other part of the integrand. All right, so, and how would I know that? Well, I'd have to reason through it. And in a lot of cases, it's a matter of kind of deciding what it's not first before you sort of realize what it is. And you may look at it and say, okay, I guess it's another integration by parts, and then you try doing that, and that falls apart almost immediately, because if you were to say, all right, I'll let x be my u, and then the 1 over the square root of 1 minus x squared be my dv, that would actually kind of take you in a big circle. So it actually might get you there, but the simpler way to do it would be the the way that you want to go. Right, so we would use U-substitution here. So I'm defining a new U, all right? So something different from the U that we defined earlier.
It's like a beauty magazine.
So
So funny.
So I'd let my U be equal to 1 minus x squared, making du equal negative 2x dx. All right, and so we think about what we have and what we need. And you gotta kind of take stock of the situation. I know that I'm replacing the radical, instead of 1 minus x squared, it's gonna be radical u, so I'm not worried about that. It's everything else. It's the negative, the x, and the dx. I want those to go away. I mean, I'll settle for just the x and the dx. I'd like the negative also to go away. And you could see my equation here, my differential equation is very close. It's only off by a 2. Okay, so divide out the 2. So we'd have 1/2 du equals negative x dx. All right, so I'd be looking, I'm just going to rewrite the entire right-hand side. X arc sine x. Then it's going to be plus, because that negative is about to go away. 1/2 times 1 over the square root of u du. I just moved some things around strategically, but I'm taking the 1/2 du and putting it together with the 1 over the root of u. Right, so just trying to put it in a way that sort of logically made sense. Or at least notation-wise made sense. And I'll do one better here, make it 1/2 u to the negative 1/2 du, so that it fits the nice power rule format. So that's going to be u to the 1/2 plus c. Then we could swap out our u for what it truly is, which is the 1 minus x squared. And so that's your mega combo problem right there. And that's a variation of your antiderivative rule, because there are other forms of it, but that's generally it. So, you know, I don't know too many people that are adding that to their list of things to memorize. When you think, okay, well, I'll memorize the derivative and antiderivative, sine, cosine, tangent, and all that. Throw in arc sine? Nah, I don't think so.
Are we allowed to leave off the C, like the very last step?
Yes.
Can
Correct.
we just like,
Yeah, except when you're on the non-calculator part of the exam. Yeah. Therein lies the problem.
They would put a question like this in the non-calculation.
They can make you,
Yeah.
yeah, make the
I love
integral
that.
of it. Sure, why not?
Thank you.
You just did it.
Yeah.